Hello. If anyone feels that they want to join, they're more than welcome to. We are going live for the first time this semester to teach you all about basic experimental design. So let's start. Let's start with some basic learning objectives. So the learning objectives are expectations from me to you, what I hope you will get out of this video. So here we are. So the first thing I hope that you'll get out of this lecture is to understand the relationship between the concept of a confounding variable and internal validity within a basic experimental design. I also hope that you will be able to describe the difference between a post-test only design and a pre-test post-test design, and be able to articulate some of the advantages or disadvantages of each of these designs. We'll also be able to contrast the difference between what's called an independent groups design and a repeated measures design, and be able to identify whatever the advantages or disadvantages of each of these designs are. And finally, we'll describe what a matched pairs design is and some reasons why you might want to consider a matched pairs design in your research. So let's start from the top. The first issue that we need to understand is why do an experiment? Now, earlier in the semester, we talked about the difference between experimental and non-experimental methods. And the one major advantage that you have with an experiment is the capacity to say that variable X caused changes to variable Y, or in other words, the independent variable caused changes to the dependent variable. As a reminder from earlier in the semester, the independent variable is referred to as the variable that you manipulate. And in order for it to be an independent variable, it must have the capacity to be manipulated. So, and by definition, a variable must have at least two or more conditions or levels. So in order for something to be a variable, it must have the capacity to vary. So when we talk about the independent variable, it must have at least two groups. The dependent variable is the variable that we measure. So this is usually the effect of our manipulation or the outcomes variable. And other than the independent variable and the dependent variable, we want to make sure that everything else is treated the same or as equivalent as possible. So we do this in two ways. The first way is experimental control, and you may recall from earlier in the semester, experimental control requires us to keep everything the same other than the independent variable. However, there are times when people bring in their unique differences or individual differences. So how do we neutralize the effect of individual differences that people bring into a study? Randomization. And you're going to hear all about random assignment. So the way we put our participants into groups must be in a fair and unbiased way. So we manipulate the independent variable, we measure the dependent variable, and we get rid of confounding variables through experimental control and randomization. In the event that you have a statistically significant outcome and you did all of these things, then you could say that the independent variable caused the changes to the dependent variable in our particular study. All right. So internal validity, you may remember this from lectures 4 and 5. Internal validity refers to our ability to say A caused B. So in order for us to have internal validity, the independent variable must be the cause to the changes in our dependent variable. So, and internal validity only occurs when you get rid of confounding variables, as we talked about. Now, just as a review, what is a confounding variable? Well, you might hear a confounding variable referred to by some professors as an extraneous variable or a third variable. And a confounding variable, extraneous variable, or third variable is any other factor other than the independent variable that could have resulted in the changes in the dependent variable. If you have an outside factor that could explain these results, that is a threat to your internal validity. That is a threat to your ability to say A caused B, or independent variable caused our changes in our dependent variable. So understanding the relationship between internal validity and confounding variables, you have to eliminate the impact of confounding variables to say A caused B, or to suggest you have internal validity. The more doubt you have about confounding variables, that increases your threat to internal validity. So let's take an example, right? So let's say you designed a study and you were exploring whether crowding had an impact on cognitive performance. And by crowding, we're defining crowding as number of people in a room. So in one condition, you had low crowding or no crowding, very few people in the room, very spaced out. And in the other condition, you had a larger amount of people in a room. So that's crowding. So what did we manipulate? Well, we manipulated the amount of crowding in a given room. So there are two conditions. And then let's say we gave them a cognitive task. Let's say it's a mathematics quiz or a memory task, something of that nature. And in the crowding group, let's say people got a 50 on it. And in the no crowding, or what I say is the low crowding group, they got a 96. So the fewer number of people in the room, they did better than the people who had a bunch of people in the room, or a larger number of people in the room. Can we say that the test scores are best explained or attributed to the differences in the crowding? So I want you to think about that question for the time being. Well, spoiler alert, the answer is no. We cannot say that it was the crowding that resulted in the change in test performance across the two groups. Now, why is that? Well, it's simple. Because we didn't take any effort in addressing potential confounding variables, they could be there. So what are some other factors that could have impacted a cognitive task? Well, temperature in a room. What if in the no crowding group, it was room temperature, anywhere between 68 to 72 degrees. But in the crowding group, it was 90 degrees. Now we have a question, was it really due to the fact that there were a larger number of people in the room? Or was it due to the temperature in the room? And because we're not sure what was the causal factor, it becomes a threat to our internal validity. So in this example, the temperature in the room could become a confounding variable. A second confounding variable could be lighting. Let's say that we did the test in two different rooms, and in the no crowding group, the room was well lit and people could see easily. And then in the crowding group, there were no windows in the room, and it was more dimly lit. Now, maybe the people in the crowding group perform poorer because of lighting and not really because of crowding. And those are just two examples of outside factors that could impact your results. Here's the deal. there is an infinite number of potential confounding variables. So if you don't take the steps we mentioned earlier, then we have a problem. And as a reminder, what are the steps? First thing is systematic control. You want to treat your participants the same. The only difference that in treatment of your participants should be your independent variable. So that's the first thing. And remember I said, what about the individual differences that people have? Randomization is very important to neutralize those. So if we kept the temperature the same, the lighting the same for all participants, then they could not have had an impact on the results. And if we randomly assigned people to the group that had no crowding and the group that had crowding, then we could have neutralized the inherent differences between people. But because we didn't do that, this particular study, we're not ready to say crowding or increased crowding impacted test results. So that's a point where I want you to pause and review, and then, but I'm going to continue. So pause the video, take note on the relationship between independent variable, dependent variable, confounding variables, and how that impacts internal validity. Okay. So now let's talk about some designs. For there to be an experiment, a true experimental design, we must have random assignment, as I said. And as you may recall, random assignment is how you put an individual into a given group. How you place participants into a group should be fair and unbiased. So the first design I'm going to introduce you to is what's called a post-test only design. Now, before I get into this, I want to highlight the concept of the post-test is referred to as a measurement of your dependent variable. So if you hear the term post-test only, that means you're only measuring the dependent variable after, post-test, after you introduce your independent variable. But I'll get there. So let's go through the steps. The first step of post-test only design is random assignment. Now, what happens if you don't do random assignment? Well, you could have what we refer to as selection differences. And if you have selection differences, that is a problem. It's possible that there is a bias from the beginning. Because what if you put all high-income people in one group and all low-income people in another group? Could that have profound effects on your results? Of course it could, right? It affects one's experience in life and one's ability for support and one's external stressors. There's so many factors. So if you don't do random assignment, you introduce the concept of selection differences or biases even from the beginning, and certainly that would be a flaw in your methodological design. So let's assume you did, though. You did random assignment. The next step is to introduce your independent variable. Now, you may recall that in a basic experiment, you're going to have two levels to an independent variable. So in this context, you would have a treatment group and a control group, or you might hear it referred to as an experimental group and a control group. Or it's possible, depending on the design, to have two different treatment groups, just you're comparing the differences. For example, you might look at reduction of anxiety using cognitive behavioral therapy versus psychodynamic therapy. Well, if you have random assignment, then you introduce these different modalities and then you measure the outcome, you could compare differences between multiple treatments. But the basic experiment, the most common scenario is that you have an experimental group and a control group. The experimental group receives the intervention or treatment, hence why on this slide it refers to as treatment, and the control group receives nothing. And the whole purpose of the control group is to serve as a comparison group. So you compare the difference between receiving the intervention versus receiving nothing. And if your independent variable, if your treatment's effective, we would expect statistically significant differences between the groups. So that's part two. Part one, random assignment. Part two, introduce your independent variable. And I said to you that this is referred to as a post-test only design because you're only measuring the dependent variable once, and that occurs after introducing the independent variables. So notice number 3, it says measure the effect of the independent variable on the dependent variable. So if you have statistically significant differences between groups and you did this, then you could say A cause B. If you have non-significant differences between the groups or identical outcomes, then you can say that your treatment was ineffective. And we could talk about what you do or what that might mean if you have non-significant differences between the groups another time. But in this particular case, I want to introduce you to standard notation as well. So you'll notice in number 1, random assignment is notated as an R. A capital R stands for random assignment. And then you're going to put arrows, one going up, one going down, to talk about the 2 groups you have in a basic experiment. Then in terms of a basic experiment, the treatment or experimental group, you'll notice that it receives an X as its standard notation. The control group will either receive an underscore or it will just be left blank as in nothing, right? So the control group doesn't receive the intervention. It receives nothing and serves as a comparison. Now, pay attention to the dependent variable and the standard notation for the dependent variable, O. So O stands for an observation or measurement. Now, in this context, how many times do you see O? Well, you see it once, right? So if you have multiple observations, then you would number O1, O2, O3, O4, and so forth. You're going to see that as we progress in later lectures. Okay. So let's talk about static groups design. Remember, you could have selection differences. So the term static groups design is another way of referring to an experimental design that doesn't have randomization, right? So if you don't have random assignment, you have static groups. And if you look at this treatment or this notation, you see XO blank O, right? So where's the R? There's no R, right? So there's no random assignment to the treatment group as an X, or an R before the underscore. There's no random assignment to the control group. Now, let's say you use this design without random assignment. And let's say we get lower depression rates in the treatment group relative to the control group. In a static groups design, can you say that the therapeutic intervention was effective? The answer is a resounding no. Without randomization, then there's any number of selection differences or confounds that could creep into your design and affect your outcome. So the answer is no. And here's just another example of a post-test design and what it should look like. Now you'll notice you have a big pool of participants, and you have these R's, these arrows going to the experimental group and the control group. And you'll notice that because it's a post-test only design, there are 3 steps. Step 1 is random assignment with the R's. Step 2 is the introduction of your independent variable, your experimental group, which receives the treatment, your control group that doesn't. And then we measure the effect of your manipulation on your dependent variable, and that's where you have your O's. Okay, so that is a post-test only design. Now let's compare a post-test only design with a pre-test post-test design. When we do a pre-test post-test design, remember what I said about the term post-test. That's referring to when you receive or you measure the variable. So you measure the dependent variable. So if you have a pre-test and a post-test, well, how many times are you measuring the dependent variable? Twice, right? You're measuring it beforehand, hence the term pre-test, and you're measuring it after you introduce your independent variable during the post-test. So in a pre-test post-test design, you measure the dependent variable at a minimum 2 times. So same rules apply. You need to have random assignment. So you'll notice the scientific notation that was discussed earlier is still relevant here. So again, R stands for random assignment. Now you'll notice that there are sub symbols, E and C. So RE stands for a random assignment into an experimental condition, and RC is a random assignment into a control condition. And then after you do your random assignment, you do your pre-test. Now remember, the pre-test is measuring the dependent variable, and every time we measure the dependent variable, it is depicted with an O. So you'll see O1. Now, we wouldn't have had to number this unless there were multiple observations. So in part 2, you have O1, there's your pre-test. Then phase 3 of a pre-test post-test design is to introduce your independent variable. Now you'll notice this symbol X was a symbol for your treatment or your experimental group, and the underscore was or blank is a symbol for your control group. Now, after you introduce your independent variable, you're gonna wanna measure the effect of your independent variable on your dependent variable a second time. So that second O, or O2, is symbolic for the post-test. Now, what's the benefit of having a pre-test? Well, in the post-test only design, we said that we do 2 things to assure that there is equivalence, right? One thing was to treat the groups equivalent other than your independent variable, but we recognize that there are individual differences, and we neutralize the effect of these individual differences through random assignment. And what's interesting is in the post-test only design, we relied on random assignment to do the job. Doing a pre-test and comparing equivalency in advance is another check and balance to make sure that the groups, before you introduce your independent variable, are the same or very similar. Now, another important point about random assignment is that in order for random assignment to work effectively, you have to have a minimum between 20 to 30 participants in each condition. If you don't have that number, then you have a concern that your sample size is low and there still could be some individual differences happening. So if you doubt the success of random assignment, you might want to do a pre-test post-test design. Now, your slide says anywhere between 20 to 30 participants. Typically in studies that I conduct, I require a larger sample which is 50 participants in each condition. So now when we look at this, you have an experimental group, you have a control group, 50 participants per would be 100 participants. So that's your pretest post-test design. Now, so what's the advantage of a pretest post-test design over a post-test only design? Well, one advantage of the pretest in the pretest post-test design is that you can guarantee equivalence or assess equivalence with a smaller number of participants. So if you're doing a study that requires a lot of money invested in a particular participant, so let's say, and COVID, right? So during COVID, each participant in these phase 3 trials, well, they cost a lot of money to administer the drug, to take care of them, to address potential side effects. So you want to make sure that your money is well spent. Now, obviously, in the COVID example, there are tens of thousands of people volunteering for these human trials. But I give that as an example because money could be a factor. So if you can't afford a large number of participants, make sure you do a pretest to make sure that there's equivalency. Another cool thing about a pretest is that you can use a pretest to select participants or to exclude participants from a study. So let's talk about that. Let's say I was studying depression and I wanted to study the impact of an intervention on depression. I need to know that the people who are in the study actually have depression. So I'm going to use a pretest to have a cutoff score. If they don't have this level of a depression, then they wouldn't be included in the study. So you can actually use a pretest as a screening measure or a criterion measure. Now, you can get an idea of where people stand before intervention as well. And lastly, you can compare in sort of a repeated measures design changes from before to after. So not only do you want to make sure the groups are equivalent, but you can measure differences between the pretest and the post-test. So an example I give there is smoking or smoking cessation study. You might want to make sure the groups are equivalent from the beginning, but that doesn't mean that the people who received cognitive behavioral therapy versus the people who received nicotine gum are going to have the same amount of change based on that intervention. So you might want to compare pre-test to post-test to see the impact of each intervention. Another factor that you have is mortality. Every study that goes on for a long period of time has dropout factor. Every study, participants either get bored and they stop participating, they move out of town and they stop participating, they change their email addresses, you can't find them. So if you're following people through time, you have to deal with the fact that people are going to drop out of your study. Now, if you don't do a pretest, you will not know why they dropped out of your study. You won't know why. If you do a pretest and you discover that there are people dropping out at higher rates in one condition over the other, then you could explore, well, what is it about that condition that created differences in people staying versus going in the study? So it's quite helpful to see or to assess potential noise in your data or error in your data. So now, does that mean you can eliminate the dropout factor or mortality in your study? The answer is no, you're not going to eliminate it entirely, but you can assess it. You can measure its impact. Now, if people drop out roughly the same across both groups, you're a happy camper because then it's nothing to do with your design. But if they drop out due to your manipulation, then you need to really think about what that's all about. All right. So what are some disadvantages, right? Because every research design has both strengths and weaknesses, advantages and disadvantages. And I'm sure you recall from lecture 6 and lecture 7, the whole purpose was to talk about strengths and weaknesses of each design. So that's a common theme. No matter what approach you take in research methods, there are going to be strengths and weaknesses. So now let's talk about the disadvantages of a pretest post-test design. So some potential weaknesses. Well, the first issue is that it's time consuming and awkward. So if you have participants who only have to be part of a study one-off time, that study is going to go more naturally and more easily than if they have to be followed through time. So having a pretest and having a post-test, it becomes challenging because you're requiring more time from both the researcher and the participant. You also are doing a dance with administering a pretest and a post-test, because when you have a post-test, it's possible that your participants might remember the questions from the pretest. And that could create greater awareness about what your hypothesis is. It could create problems around them wanting to tell you what you want to hear. So the second problem, as I'm mentioning, is you could sensitize your participants to what's being studied. Now, you may not realize the power you have on your participants. As a researcher, they see you as an authority figure. And most people seek to obey authority. Most people will follow direction. So if you have a participant who figures out what the true nature of the study is, they might start to answer the question in accordance with what you want or what they believe your hypothesis is, rather than their true answer. Now, what does that do? That skews your results, right? It creates bias, and it creates problems between those who had a pretest versus those who didn't have a pretest, and whether you can generalize from your study to the real world, right? So it's a problem, the pretest, but is there anything you could do about it? The answer is yes, of course you can. One strategy people do is they embed completely irrelevant tasks in the experimental procedure just to throw you off the trail. So you might have a pretest, but you might have other activities, and you won't know that those other activities have nothing to do with the study, just it's busy work or filler. So that's one thing you could do. You can embed irrelevant tasks, or you could disguise it so that it's not detectable. Long story short, if you're going to do a pretest, you know that you have the problem with sensitizing your participants, so you're going to have to figure out how to reduce them figuring out what your hypothesis was. All right. So I mentioned that there is something called a basic experiment. And in a basic experiment, you typically have two conditions. You have an experimental group and a control group. But there are times when you might have more than two groups, right? You might have 3 groups, you might have 4 groups. There are studies that have 5, 6, 7 groups. Most drug trials have a lot of groups to compare nuance between dose, nuance between different medication, nuance between placebo effect, and nuance between real effect of the manipulation. So here's the notation. Remember, every experiment must have random assignment. So once again, You have the R's. So R stands for random assignment. Afterwards, you have the pretest. So you see the number 1. And then it's interesting, with 3 or more groups, you can have multiple treatments. So the control group stays the same as this blank space, but look at this. You have X1, X2. Well, X stood for treatment. X1 would stand for treatment 1. X2 would stand for treatment 2. So now we can compare difference in effectiveness between the control group and multiple treatments. So I asked, when would we use this type of design? It's pretty simple. When you have drug trials is the most common scenario where you want to have 3, 4, 5 groups. But I'm trained as a clinical psychologist, so I'm also interested in the effectiveness of different treatment modalities. So you might have a group that just has basic reading about a condition, which we call psychoeducation. You might have a group that has cognitive behavioral therapy. You might have a group that has psychodynamic therapy. You might have another group that does rational and motive behavioral therapy, and so forth. And then now we can compare the outcomes of people who are untreated, right? Versus people who are treated with one form of therapy versus another form of therapy. And then we can say with greater certainty that treatment approach X works better than treatment approach Y. So just going back to the question at the bottom of the slide, when would one use this? When we're trying to separate in drug trials the difference between the control group and other conditions. We're trying to assess placebo effect versus real effect and so forth. Or if we're doing therapy, the effectiveness of given interventions. So now we talked about the concept of a pretest, and we talked about the problem of the pretest potentially impacting how people behave, right? So there's a term for that. That's called a pretest effect. If the pretest impacts or changes a person's response on the post-test, that's called a pretest effect. Well, how do you know if you have a pretest effect or not? Well, there's another design, and I know in Lecture 8 you have a bunch of designs, so I'm throwing a lot at you, but feel free to pause this video to separate the differences. So in a Solomon 4 groups design, it's called Solomon 4 groups for a reason, right? There are 4 conditions. You have 2 control groups and 2 treatment groups. You have 2 groups that are pre-test, post-test, and you have 2 groups that are post-test only. So now in this design, you can actually measure and determine whether you had a pretest effect. This is a really, really cool thing. So if there was no pretest effect, then the people who received the pretest versus the people who didn't receive the pretest should not differ on their measure. But if there was a pretest effect, you'll see a change in outcomes as a function of that. And here's your scientific notation, right? So you'll notice O1, O2. So all groups are receiving a post-test, but I said 2 of the groups are going to receive a pretest. So this is one group receiving a pretest. This is a second group receiving a pretest where you see O1. 2 of the groups are not going to receive a pretest, so it's left blank. And now because it's left blank, the blank notation can't mean control group. So for that, we number 1 and 2. So X1, you would write in notes in the study that X1 stands for control group. So we have the first two groups are control groups, one of which had a pre-test, post-test design, one who had a post-test only design. Group 3 and 4 are our experimental group. Notice the treatment shifts from 1 to 2, so it's a different modality. Now they're receiving the intervention. And in the treatment group, you have, or the experimental group, you have a pre-test, post-test group, that's number 3, and then a post-test only group. So here you have 4 groups, 4 modalities. And if you look at your table, it depicts it in another way, right? So if you look over here, you see the independent variable control group versus experimental group. Those of you who came in later, the experimental group I refer to sometimes as a treatment group. Control group is a control group, it's a comparison group. So you have divided by control versus experimental or treatment group, and then you have your post-test only and your pre-test post-test, and count the number of squares you have. 1, 2, 3, 4. So when we say Solomon 4 groups design, this is what it looks like in scientific notation and in a tabular form. So let's apply this example. Suppose a person wanted to see if the Kaplan review course helped GRE scores. Now you'll notice this is Kaplan, K-A-P-L-A-N, and I am Kaplan, K-A-P-L-I-N. So there's no relationship there, although I do wish they would adopt me. But the Kaplan review course is basically a prep course to help people prepare for taking the GREs. So we randomly assign people into either receiving this training course or not. So half the people receive the training course, half the people do not receive the training course. The people who do not receive the training course, they're in a control group. The people who receive the Kaplan review course, they're considered in a treatment group. Now we have the experimental versus control group. We also have 2 groups who are tested on the GRE before the course is given, and then they're allowed to take the GRE a second time after the review course. And then we see, well, what happens after 3 weeks of training of this Kaplan review course? Let's see what happens. So I said to you, there is the potential for a pretest effect or no pretest effect. Well, let's take a look at outcome 1, which has no pretest effect. Now, we have the control groups. Remember the control groups, these are the people in the hollow white bar who did not receive the Kaplan review course. And then in the gray shaded bars, these are the people who received the GRE training. Now, we see in general that the people who received the GRE training did better than the people who didn't receive the training. So if we have this outcome, we would say, well, the GRE training was effective in increasing performance on the GRE. Now, what you'll notice though, is those people who were post-test only versus pre-test, post-test. Let's compare those individuals. So let's compare the white bar to the white bar. These are both people who are in a control group. You'll notice no significant differences between the groups, whether they received the pre-test or not. And the same thing could be said with the gray bar. Compare gray to gray. The treatment group, those people who received the GRE training, the same again. So if we had a pretest effect, there should be a difference between the gray bars or the white bars from one another. So now let's see what a pretest effect would look like visually. So outcome 2, this is when somehow taking the GRE twice helped you rather than the Kaplan course itself. So let's compare the control group. These are people who did not receive the training. Identical, so far so good. We're not seeing a pretest effect yet, but if we compare the gray to the gray, post-test only versus pretest post-test, you'll notice even though both groups in gray received the Kaplan review course, the training, the GRE training, the people who received the pretest post-test design, that pretest increased the performance more than those people in gray who only did the post-test. So now that would be a very good example of a pretest effect, because it wasn't really, in this case, the Kaplan review course alone that caused this change. It was the pretest coupled with the Kaplan review course that resulted in that spike circled in red. So again, a pretest effect impacts your results in an adverse way. It's a bad thing. It's problematic. So we don't want to have a pretest effect. But the beautiful thing about a Solomon 4 groups design is that you have the ability to assess whether there was a pretest effect. And that's Solomon 4 groups. So I'd like you to pause the video for a moment, draw a line in your notes, because I'm going to shift gears in terminology. So far, we talked about the concept of basic experiments. We talked about internal validity. We talked about the independent variable. We talked about the dependent variable. We talked about confounding variables. And then we talked about the difference between a post-test only design versus a pretest post-test design, right? So that's where we are. So if you're keeping score of the objectives for this lesson, we've covered 2 of the major objectives so far. So now I'm going to shift gears to other terminology referred to as an independent groups design versus a repeated measures design. Now, I put in parenthesis other terminology, and I think that this terminology is going to be helpful for you when you take statistics and when you take your lab courses, your experimental course, because the terminology means something. So let's start with an independent groups design. An independent groups design is sometimes referred to as a between subjects design. What does that mean? If you have different conditions or different groups, a participant only participates in one of the conditions. What would that mean? So if we go back to earlier in this lecture, we talked about crowding versus no crowding and test performance. A participant would either be assigned to the crowded group or the no crowded group, but not both. So in independent groups, each group is separate and distinct from one another. The participants are different from one another. So we will also refer to as this between subjects design. Now, one of the things that you need to do, regardless of what you're doing, is you need to have random assignment to address potential problems or biases. So if you have random assignment and you put people into different groups, that will neutralize systematic biases. It will eliminate systematic biases. So that's the first thing. Now, when you compare differences between individuals, I expect everybody in this class to be different from me and different from one another. In fact, when you take developmental psychology, you will see that even identical twins have differences from one another. They have similarities, but they're not perfectly the same. So when we say between subjects, we expect there to be natural differences between you and me. So we're comparing differences across groups, but across people as well. Whereas when we refer to a repeated measures design, that's sometimes referred to as a within subjects design. And a within subjects design, that means the participant who is selected for the study is going to participate in all the conditions. Now, who are they being compared against? The answer is themselves. So when we talk about a within subjects design, we compare your performance on one task relative to your performance on another task, or your performance at one point in time versus your performance in another point in time. Now, while we expect real and meaningful differences between people, we expect you as a person to be relatively stable within yourself. We expect you to be stable within yourself. And that's the case, right? When we study personality, we expect people to have behaviors that are relatively predictable or consistent. And in fact, there's a whole class of disorders called personality disorders. And the hallmark feature of personality disorders are an unstable sense of self, or how you become erratic in your behavior relative to whom? Yourself. You become unpredictable. So in a repeated measures design, we're comparing you relative to yourself, or you within yourself. So independent groups design, different participants for the different groups. Repeated measures design, the participant participates in all of the conditions of the independent variable. Aaron. So let's do an example of what this might look like if we were doing a memory task. And the first example I'm going to do, and I use the same numbers for a reason, and I'm going to talk about that as I go. Let's start with an independent group design and recall. So what would this look like? We give people word pairs, and we ask you to memorize the word pairs. And you're either put in a high meaning group or a low meaning group. So a high meaning group is one level of the independent variable, and high meaning means the words are similar to one another, or they might be conceptually similar. So if I give a high meaning group words that sound like this: cat, rat, dog. Well, that's going to be easy to remember because they're all animals. They're all three-letter words. They're all animals. But if I use cat, ball, tree, right? Now those become problematic for two reasons. One, the words are not, they're not thematically the same, right? So they're not all animals. They're different objects or entities. And they also have different number of letters. So that would make it less meaningful, meaning it's harder to associate that. And now we compare high meaning group, easily associated list of words, versus low meaning group, words that are not readily connected. And then we have a group of participants. Group one, that's the group of participants who have the high meaning. So we have 3 participants. And they participant 1 gets a 68%, participant 2 gets an 81%, participant 3 gets a 92%. What we're going to do is we're going to compare the average of the participants in the high meaning group versus the people in the low meaning group, right? So participant 4 gets a 64%, 5 gets a 78%, and 6 gets an 85, for an average of 75. If we compare the two groups, high meaning versus low meaning, on the averages, we would see a difference with high meaning group average being better than low meaning average. Now, here's the deal. Embedded in this design, you'll notice that for this particular graphic, there are 6 participants. 3 participants in the independent groups, 3 participants, 3 participants in a high meaning group, and 3 participants in a low meaning group. That's what an independent groups design are. There are different participants in each group. Now, let's compare that to repeated measures. Now, if we compare the number of participants, we have 3 participants. And it's the same participants being given a high meaning list of words and a low meaning list of words. And then now, instead of comparing the averages of one group versus another group, now we're comparing the differences of a participant within him, her, or themselves, right? So you'll notice that participant 1 got a 68 in high meaning. On low meaning, that same participant got a 64. So that's a +4 or a difference of 4 higher percent in the higher meaning. Participant 2 got an 81 versus a 78. When we compare the difference, we're going to see a +3, right? Because 81 minus 78 is 3 more in a high meaning group. And then participant 3, 92 versus 85, that 92 in the high meaning group is 7 greater than 85. But notice in the repeated measures design, the same participant goes through all of the conditions of high meaning and low meaning. Whereas when it was an independent groups design, there were different participants in each of the conditions, different participants in the high meaning group versus low meaning group. Now, this may seem like a nuance, but when we talk about statistics, guess what? There's something called an independent samples t-test and a repeated measures or dependent samples t-test. And for the previous slide, you would use an independent samples t-test to compare the differences in the average and high meaning versus low meaning. Whereas in a repeated measures, you would use a dependent t-test and we would compare the differences and whether there are significant differences from high to low within a given participant. So, as with earlier in the lecture, I said every design has strengths and weaknesses. So what are the advantages of a repeated measures design? The first thing you notice is that there are fewer number of participants necessary to do your study. And as I mentioned earlier, the number of participants and sample size matters, right? Because as you increase sample size, your confidence in an outcome increases. But if you don't have the money for a large sample, with a repeated measures design, you can get the same data with fewer number of participants. So in the memory task that we talked about, to get the same comparison, we needed 3 participants in a repeated measures design, whereas in the independent samples, independent groups design, we needed 6. The other thing that I alluded to is that when we talk about independent groups, we expect there to be natural differences between you and me, naturally. So it's hard in an independent groups design to truly know whether the differences are due to real or meaningful differences in the independent variable or how people are placed in groups. So that's what we call random error. If it's due to how people were placed in groups, not due to my manipulation, that's error. When it comes to when it comes to repeated measures design, you decrease the amount of random error because I expect you to be relatively consistent within yourself. So your memory is your memory. So we're not comparing your memory versus someone else's memory in a repeated measures design. We're using your memory against itself in with a manipulation of high meaning versus low meaning. So repeated measures design reduces the amount of random error, which has a cool outcome. Smaller differences between pre-test and post-test, or condition A and condition B, are statistically significant. So when it comes to repeated measures, it has a greater sensitivity to smaller differences from condition to condition. What are the drawbacks? Well, when you give people multiple conditions, you have to worry about sensitizing your participants. So one of the disadvantages that we talk about is what we call an order effect. An order effect is, it's instead of the manipulation being what happened or causing the changes to the dependent variable, it's to the sequence or the order by which you put people through the conditions. So if every single time you did the high meaning first and then the low meaning, well, maybe people got tired. Maybe they didn't want to do 2 memory tasks, or they got exhausted. So at that point, it's possible that you have what's called a fatigue effect. So because they did 2 tasks of memory, the second task was negatively affected. But let me explain each of these. A practice effect is repeated exposure to a task could increase performance. Remember the phrase, practice makes perfect. Well, the reality is practice makes proficient, not perfect, because there is no such thing as perfection. But a practice effect, the performance would increase. So if I give you a math test and then I give you the same math test a second time, the practice from the first test could improve your performance on the second test. We also have a fatigue effect, which could be the problem here if you didn't address the order effect, where repeated exposure to a task makes it worse or causes you to perform more poorly. So I'll give you an example, a very simple example of weightlifting. People tend to perform worse at the end of their exercise routine than at the beginning because they have muscle fatigue. The same thing can be said about cognitive tasks. You can also have fatigue. Or if you're watching Zoom videos, you can zoom out or do what one of my friends calls become a zombie. Not a zombie, but a zombie, where after a certain amount of the lecture, you just lose focus. So that's a fatigue effect. So we talked about practice effect, repeated exposure increases performance, fatigue effect decreases performance. And then there's a contrast effect. One of the cool things about human beings is that we have the ability to compare and contrast things and find patterns in behavior. So it's possible we might know what you want from us in the second data collection by comparing it to the first data collection. So the first treatment could impact the second treatment. So all 3 of these effects are forms of order effects: practice, fatigue, and contrast. So what can you do? How do you handle order effects? One suggestion given, and I'm not going to go through all of the formulas when we talk about Latin square, but I'm going to just explain it conceptually because that's all you need to know for this class. So one way to address order effects is to do counterbalancing. The concept of counterbalancing is that some of the participants will go in one order, other participants will go in a different order. So when it comes to the memory task, there needs to be participants who first had high meaning, then low meaning, and then other participants who had low meaning, then high meaning. So notice how some are first receiving one order, then the other, and then other participants start with it reversed. When you have two groups, you can do complete counterbalancing. Now, complete counterbalancing, I want you to underline the word complete, because that implies that every possible order is addressed. Well, that might be easy to do if you have two groups or three groups, but as the number of groups in an independent variable increase, it becomes much harder. So the mathematical calculation to see how many orders or sequences you need is the factorial of the number of groups. So 2 factorial is 2 times 1, right? So 2 times 1 equals 2. 3 factorial is 3 times 2 times 1. That's how we got 6. 3 times 2 is 6, times 1 remains 6, and so forth. But let's say you had 10 groups. Now I'm going to go onto my calculator on my phone, and I'm going to tell you how many different orders there would be. So if there were 10 groups, you would need 10 factorial. So that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And I'm going to ignore times 1 because it stays the same. But I'm going to put the number here. If you look at my calculator, it says 3,628,800 different possible orders of presentation. Well, if you had 10 groups, you're not going to be able to do complete counterbalancing because you won't even have that many participants. In good studies, you might have 200-300 participants. 3.5 million participants? Obviously, we have to have another way of doing counterbalancing that isn't just complete counterbalancing. So this is an example of 2 different orders, right? So if you're going to do a repeated measures design, so one group receives in order 1, low then high, the other group of participants high then low. So you flip the sequence. Easy with 2, right? Because it's only 2 conditions. But when you go up to 10 conditions, now you have 3.5 million potential sequences. You're not going to do that. So the good news is that there were mathematicians who figured out another way of doing this. When you cannot do complete counterbalancing, it's recommended that you do something called Latin squares. Now, Latin squares design allows you to flip the orders of presentation. It allows you to have each intervention in each of the different serial positions, and it allows you to have each intervention before and after everyone else. So before and after the other conditions. Now, the number of orders or sequences is equal to the total number of conditions. Complete counterbalancing. If you had 10 conditions, you needed 3.5 million orders. With Latin squares, the number of orders is equal to the number of conditions, so you'll only have 10 different sequence patterns, which reduces it in a way that makes it more meaningful. I'm going to skip this slide. In class, I would do it on a board and have you do the grid, but you don't need to know this, right? So let's just demonstrate with if you have 4 conditions or 4 orders, right, how a Latin square would work. So if you have 4 conditions, we're going to call it condition A, B, C, and D. Now, you'll notice the first row is A, B, D, C. That's your first order. Now, as you go down, you just rotate your letters. A becomes B, B becomes C, C becomes D. B becomes C, C becomes D, D becomes A, because once you get to the last condition, you have to go all the way back to the beginning, and so forth. But now let's look at A. Does A come before B? Sure it does. A becomes before B in row 1. Does A come after B? So here it's before, Here it's after. Does A come before C? In row 4, A comes before C. Does A come after C? In row 2, C, then A. Does A come before D? And when I say before, immediately. So in row 2, you have A, then D. And then in row 4, D, then A. And you could do this with all of the letters, but what you notice is that this formula flips the sequence around in a meaningful way that A, or point 1 is that not everyone is getting the same sequence. And point 2 is that the sequence are randomized in a way that each each condition comes both before and after another for a particular set of groups. So Latin square is a brilliant way to deal with order effects when you can't do complete counterbalancing. So controlling order effects, another way to do it other than counterbalancing is to allow time to pass. So the longer the time that passes between measurement A and measurement B, the less likely that you're going to be able to benefit from A to B for a practice effect, or the less likely it's going to be that you're going to be tired out from A to B because you have a rest period. Now, when it comes to a contrast effect, you want to address this by having busy work in the middle. So have some unrelated task so that they can't connect task A to task B. It could be as simple as asking them to say the alphabet or say the alphabet backwards if they can. That requires enough mental energy to distract them from linking the two. All right, now, what are the problems? Well, you have to deal with the potential that the longer the time a person agrees to participate, the less likely they're going to want to volunteer. Moreover, even if they start, they may not continue to the end. So if you're going to extend the time interval, be mindful that the longer you extend the time period, the more likely people are going to say, yeah, no, I'm not doing that, or say, yeah, I'll do it, but quit somewhere in the middle. So which one is better? Now, that's a trap question. The truth is, it's not which one is better. Which one is better for you based on the situation you're trying to do? There are strengths and weaknesses to both of them. So what's the benefit of an independent groups design or between groups design? Well, you don't have to deal with counterbalancing. You don't have to deal with order effects. You just participate in your one part of the study and you're good. So you don't have to deal with order effects. What's the benefit of repeated measures design? Well, I mentioned that you have a smaller sample size needed. Remember, 3 versus 6. Because we're comparing you within yourself, it's a within groups design, you have less error. Now, here's one time where you will never use a repeated measures design. If you have a circumstance where your intervention has an irreversible effect, then you can't flip the person to the other side. So an example might be psychotherapy. Once you went to therapy, we can't take that experience away from you. And if you've improved, we can't take that away from you for 2 points. 1, you've done better, but 2, it might be unethical to withdraw that treatment. So if something is not reversible, you definitely want to put a person in an independent groups design. And the last consideration you have is real world issues. Think about what you're studying. Is this the kind of thing that happens once in a lifetime or very rarely? If it's the kind of thing that happens once in a lifetime or very rarely, you want to use an independent groups design. If it happens often, then you might want to use a repeated measures design. So the real world issues and what you're measuring, that's something you want to think about when doing your design. And the last thing I'm going to talk to you about is something called a matched pairs design. A matched pairs design is when you match or try and make your participants equal on some participant characteristic. Now, here's the deal. Matched pairs has a matching variable. Now, the matching variable is not the independent variable. It is not the dependent variable, but it is linked very strongly to the dependent variable. So you might match people on intelligence before putting people into groups, and the dependent variable might be verbal abilities, right? Because language and intelligence are linked. So when you match people, you give all the participants your matching variable, and then you rank order from highest performing to lowest performing, and then you pair them up. So the person who did the best is in one group, and you compare them to the person who did the second best. And then the person who did the third best is then compared with the fourth, fifth to sixth, seventh to eighth, and it just rotates in sort of like a snake fashion. But now you've made the groups much more equivalent to start. And then from that point, once you have the equivalent groups, then you introduce your independent variable and you measure your dependent variable. And at that point, it has the benefit of an independent groups design. And this final slide is just a recap on the three. And that is our lecture. Now I see some people came in and I did a video straight through, and you probably had questions. So if you have questions, I'm happy to keep this going. But that's lecture 8 in a nutshell. Any questions from anyone here?
Yeah, I had a question regarding the discussion board for this week.
Sure.
So the question for the discussion board was the different from the experiment from non-experimental designs. Did you mean like the experimental group and the control group, like basically in like a pre-test, post-test, or?
Yeah, no, I'm comparing, I want you to think about what you're getting in lecture 8 versus what you are doing in lectures 6 and 7, right? So you're comparing an experiment to your observational methods, your experiment to your correlational methods. Now, spoiler alert, I will tell you that we did cover this somewhat in lecture 1. Now, granted, I didn't do the Zoom lecture in lecture 1 at that point, but the answer can be found in this lesson, in lesson 1, and in lesson 4.
Okay.
So this is not actually the first time that I've said the answer to that question, but I just wanted to lock that principle in so that when you get to the next class, you have it. So really you're saying, well, what makes an experiment different from all other forms of research designs?
Okay.
Does that help at all?
Yes, thank you.
You got it. Any other questions on the content or discussion board? Obviously, I can't react to the test just yet because it's still live, but if you have any questions, feel free to ask.
Is chapter 8 on the exam?
No.
Okay.
8 through 10 are exam 3.
Okay.
Now, what's interesting is that material does resurface, right? So the discussion board question I asked you today, you would have had that information available to you in for lecture 1 and lecture 4, but it resurfaces in one way or another. But I try and keep them blocked off in specific sections. So 8 through 10 are exam 3.
Okay, thank you.
Sure. Any others? If not, what I'm going to do is I'm going to stop the recording and then drop off. And then it's supposed to send this Zoom to the cloud, and I'll share the link with the class. All right. Okay, so I'm going to sign off. I will see you on Friday. Take care, everybody.
Thank you, Professor. Have a
Thank
good
you,
day.
Professor. Do you take attendance?
No.
Thank you. Okay,
This is not mandatory. This is me just saying I decided I should start recording lectures. And I'm like, you know what? Maybe you want to be part of that. If I
Okay.
have to sit, maybe you have questions, but it's not required.
Okay, thank you.
You got it. All right. Well, so we'll stop there.